Welcome everyone. In this video, we'll discuss problems related to absorption and fluorescence spectroscopy. So let's start with the problems. In the first question, it has been asked to calculate the concentration as well as the molarity of the protein solution. So if you can read the question, it says the molar extinction coefficients of tryptophan and tyrosine at 280 nanometer are 5690 and 1280 molar inverse centimeter inverse respectively. The polypeptide chain of spike glycoprotein novel coronavirus molecular weight given 141178, which is equal to 141.178 kilodalton, contains 11 tryptophan and 54 tyrosine residues. So this much information is given for this particular protein. Now the question is that I need to calculate the absorbance at 280 nanometer of a 0.32 mg per ml solution of spike protein measured in a cuvette of 1 centimeter path length. So what is the absorbance going to be? In the second part, they have asked what is the molarity of this protein solution. Now remember, for any material, the path length of the sample as well as the concentration is directly proportional to the absorbance of the solution. We all know the famous Beer-Lambert law, and in the mathematical expression we can represent it in the form of absorption equal to epsilon C L. L is the path length, C is the concentration, epsilon is the molar extinction coefficient. Now from the question, L is very clear, which is 1 centimeter path length given. Concentration I need to calculate. Also the epsilon value for a single tryptophan and tyrosine is given. So I need to calculate the molar extinction coefficient for this protein, which is going to be equal to how many tryptophans are given? 11 tryptophans. So that means I'm representing tryptophan with a single letter code W into its molar extinction coefficient of 5690 plus 54 tyrosine we have with a molar extinction coefficient of 1280. Y represents it's a single letter code for tyrosine. So let's calculate this value. We have 11 into 5690, which is equal to 62590 plus 54 multiplied by 1280, and we'll get 69120. So total molar extinction coefficient is going to be 69120 plus 62590, which is equal to 131710. Fine. So we have epsilon, we have L, which is path length 1 centimeter. Now we need to look at C. Now what is given in the question? They have asked us to calculate the absorbance for a 0.32 mg per ml. To calculate its concentration in a molar or moles per liter, what I need to do, I need to divide this value with its molecular weight. It's a simple molarity formula, gram moles of solute divided by volume of solution in liter. So if I need to calculate the concentration in moles per liter, I need to divide this term with a molecular weight. So given is 0.32 mg per ml, which we can also rewrite it as a 0.32 gram per liter. That means the same thing. It's just a conversion. And then I need to divide this term with its molecular weight of this protein, spike glycoprotein, 141178. 141178. And remember, it's given in Dalton. We can write Dalton as gram per mole. So 14178 gram per mole. And what is the value going to be? It's going to be It's going to be 2.266 into 10 raised to the minus 6 moles per liter, or you can call it as a molar, capital M. Fine. So we have calculated epsilon, which is 131710. We have calculated, concentration, which is 2.266, and path length, which is 1. So what is the absorbance going to be? It's going to be, we just need to do some simple mathematics. And the value which is coming is 0.298. So for the first part, the absorbance for this particular solution of 0.32 mg per ml at 280 nanometer, with this much information given, it's going to be 0.298. Fine. Now what is the second part? In the second part, they have asked what is the molarity of this protein solution. Just now we have calculated. For putting this term in the Beer-Lambert's formula, just now I have calculated, and it's coming out to be 2.266 into 10 raised to the minus 6. You can write this as a moles per liter, or you can even call this as 2.27 micromolar solution. I hope this solution is clear to each and every one of you. If not, if you do have some doubt, please comment it in the comment box. Coming back to the second question, which is from the fluorescence. And the question is, the below figure shows the fluorescence emission spectra. So they have given emission, not the excitation. It's an emission spectra of 3 different proteins: protein X, protein Y, and protein Z. And these were excited at 280 nanometer. We all know that in the proteins we have fluorophores, and those are aromatic amino acids, mainly tryptophan, tyrosine, and phenylalanine too, but phenylalanine has a low quantum yield, so generally we don't include phenylalanine for our fluorescence studies. And just to give you some idea for the excitation and emission wavelength for these amino acids, for tryptophan, we generally excite it as close to 280 nanometer, and the emission spectra is somewhere close to 330 to 350 nanometer, but we'll write it as 347 to 350. Now, what does it tell you? If the emission spectra is coming out at 347 to 350 nanometer, that tells you that tryptophan is present on the surface, and it is exposed to the solvent. That is, it is surrounded by the water molecules, polar solvent. Remember, these tryptophan specifically is very sensitive to the environment, be it polar or be it non-polar. If it's buried, let's assume if the tryptophan is buried, you are going to see the emission spectra at less than 330 nanometers. So remember, these are very, very prone to the environmental conditions, and that's the reason many of the times these amino acids are chosen for studying characteristics like protein denaturation, the structural transition, etc., or the effect of pH, temperature, and salt on these proteins. Coming back to the tyrosine, we generally excite tyrosine at close to 275 nanometer, and we get an emission spectra close to 303 to 306 nanometer. Now for phenylalanine, as I said, it has a low quantum yield, and if you look at its excitation, we generally excite phenylalanine at 258 nanometer, and we analyze the emission spectra at close to 282 nanometer. Now let's have a look at these statements, and then we need to pick the correct interpretation. So which one of the following statements gives the correct interpretation? Protein Y and Z have tryptophan. protein Y and Z have tryptophan? Could be. Could be, because this is the emission spectra coming at 330 lambda max here, 350 lambda max. So could be. While protein X has only phenylalanine. Now this part doesn't seem to be true. Protein X has only phenylalanine. I'm talking about the emission spectra. Phenylalanine generally gives the emission spectra close at 282 nanometer, and as said before, because of its low quantum yield, it is generally not considered. So the later part seems to be wrong. Second, so overall this statement is not correct. Second, protein X has only tyrosine. Protein X has only tyrosine, could be, and protein Y has tryptophan on the surface, while protein Z has tryptophan buried inside. Now Y and Z could, these proteins could be carrying tryptophan, but remember what I said just now. If the tryptophan is present on the surface and it is exposed to the polar solvent, you are going to get emission spectra more than 330 nanometer. Now remember what they have written here, the Z, where the lambda max for the tryptophan is coming out to be 350, it is telling me that it is buried inside. Now this part is entirely wrong. And also even this statement is wrong. Y has tryptophan on the surface. So Y is going to be inside it's in this protein. In this case, Y, in the case of protein Y, the tryptophan seems to be buried, while in case of the protein Z, tryptophan seems to be on the surface. So even this statement is wrong. Third, protein X has tryptophan buried inside. Protein X, they are saying it is having a tryptophan buried inside. Remember, look at its emission spectra. It seems to be more of tyrosine rather than tryptophan. So again, this statement is completely wrong. Fourth, protein X has only tyrosine. Could be protein X has only tyrosine and protein Y has tryptophan buried. Seems to be all right. Protein Y has tryptophan buried, and that is the reason we are seeing the emission spectra lambda max close to 330 nanometer, and protein Z has tryptophan on the surface. So as said, if the tryptophan is exposed to the solvent, to the polar solvent, we are going to see lambda max close to 350 nanometer. Now remember, these values are they have a particular range, and remember these emission spectra depends upon many factors. You need to consider the contributions from the nearby amino acids, the pH, salt, and other factors. So you just no need to memorize these values, because these values will differ, not too much, but will differ to some extent depending upon your experimental parameters and depending upon your experimental conditions. So out of all these, the fourth statement seems to be the correct interpretation. I hope these questions are clear to each and every one of you. If you do have questions, please feel free to comment.